In this video I'm going to explain and do a sample problem for a commonly used experimental method known as titrations. So this is basically just an extrapolation on the acid-base chemistry that I was talking about last video. Because a titration, really all a titration is, it's a very controlled neutralization reaction. So a titration, you do that when you have either an acid or a base of unknown concentration and you want to know what its concentration is. So let's say if you have an acid, a solution of acid, and you want to know what its concentration is. You take a basic solution with a very precisely known, with a very, very well known and measured concentration, and you very carefully mix the two to reach exactly the point when they're neutralized, and you can then mathematically determine the concentration of your acid. So in a titration, I do want to say one term that you want to know is something called the equivalence point. And sometimes you'll also hear this referred to as the titration point, and that is the exact point when the acid and base are neutralized. When the acid and base are neutralized. So, and if you are looking at a curve of a titration graph, it's right at the inflection point. Is basically where the equivalence point is. So when you're doing a titration, there are three things you need in solution, or well, when you're mixing the solutions. So three things necessary for titration. Two of them are extremely obvious. You need an acid, and you need a base. Right? Because obviously we're doing the neutralization reaction. The third thing you need is an indicator. So an indicator is something that undergoes a physical change at the pH that you're looking for. Because technically you don't always need to look for exactly a pH of 7, although that is definitely the most common. Now, the most common physical change that an indicator will do is a change in color. So a very common one is phenolphthalein, because phenolphthalein right at about a pH of 7 goes, so below 7 it's transparent, it's colorless, and right at about a pH of 7 phenolphthalein turns pink. So if you're trying to find exactly the point when an acid and base are neutralized, basically as soon as you see some pink forming, if you're going from acidic pH, as soon as you start to see some pink forming, that's and constantly forming and staying there, that's when you have a neutralized reaction mixture. But another important thing about the indicator, not only does it need to change at the pH that you're looking for, but it has to also have no effect on the reaction itself. So the indicator has to be there and present, but it cannot react. It can't affect the way that the acid and the base react. Right? It's basically just a spectator waiting to tell you when you've reached the right point in your reaction. Right? Now you'll see some word problems with titration reactions, and you'll have to do some math to figure out a concentration of either the acid or the base. And so I'm going to do one right now, and they'll basically all follow this exact same basic type of format. Right? So if we have 24 milliliters of 0.1231 molar sodium hydroxide, and that will react with 25 milliliters of H2SO4. What is the concentration of the H2SO4? So for the acid and the base, for one of the two, you'll always be given a volume and a concentration. and the other one, you'll only be given one of those two things, either the volume or the concentration. And whichever one you're not given both pieces of information for, you have to solve for that other piece of information. So here, for our base, sodium hydroxide, we're given the volume and the concentration, but for our acid, this is sulfuric acid, we're only given the volume. So that's why we need to find the other piece of information for the acid. Now, the one other piece of information in order to solve this that we need is the balanced chemical equation. So that would have to be given to you, or most of the time it will be given to you. It's possible I could ask you to, write out the balanced equation. So again, this is just a neutralization reaction, right? So you're writing the neutralization reaction between sodium hydroxide and sulfuric acid, and you need to make sure it's balanced. So if you want, it'd be a nice idea to pause the video now and try that yourself. Alright, so hopefully you gave it a try. If not, no problem. I'm going to just write it out here. So we have 2 NaOH plus H2SO4 there's your water, and our salt is this. Alright, so you did have the tools to figure that out based on what we know about forming ionic compounds, about a neutralization reaction, about balancing equations, but don't feel bad if you didn't get it. You'll have plenty of more practice, as we go. So the reason that so again, we had to put 2's before each of these to keep it balanced, and it makes sense that we had to do that because remember, water forms from 1 hydrogen ion from the acid and 1 OH minus ion from the base. So that means that in order for a reaction to be neutralized, we need the exact same amount of H plus ions as OH minus ions, so that we get water every single time, with none left over. Well, H2SO4, both of those hydrogens can be given off as H plus ions. In fact, not only can they are given off as H plus ions. So each molecule of H2SO4 gives off 2 H plus ions, but each molecule of NaOH only gives off 1 OH minus ion. So that means that we need twice as many molecules of NaOH so that H plus and OH minus amounts will be equivalent. So now that we know the reaction, let's work on this titration problem. Okay, so the first thing you're going to do is whichever species between the acid and the base that you're given both values of, the volume and the concentration, you want to start with that concentration. So we're going to start with the concentration of NaOH. And remember, molarity can also be written as moles over liters. So I'm actually going to rewrite it in that sense, and you'll see why. So 0.1231 molar can be rewritten as 0.1231 moles of NaOH over 1 liter of solution. Now, so the reason I did that, so remember, ultimately what we're looking for in this problem is the concentration in molarity of the sulfuric acid solution, before we mixed it with the base. So we're looking for molarity. So that means that we need the moles of H2SO4, and we need the liters of the solution. Well, we already know the volume of the solution. We're given 25 milliliters, so we'll need to convert that to liters, but we already know the volume. So as long as we figure out the moles, we can figure out the molarity. So that's what we're going to try to do here. We're converting this into moles of H2SO4. So our first step here, let's get rid of this denominator so that we are left with just moles of NaOH. Because remember, you want to get into moles of one chemical species so you can do a mole to mole ratio to the other chemical species. So we're actually just going to multiply this by the volume. But remember, the volume is given in milliliters, so we need to convert that to liters. So 24 milliliters. Remember, there's 1,000 milliliters in 1 liter. So milliliters has to go on the bottom to get canceled out. 1 liter. Those units cancel out. So we're just dividing by 1,000. That gives us 0.024 liters. Well, I'm just going to put that over 1. Units of liters cancels out. That gives us into moles of sodium hydroxide. So now we can do a mole-to-mole ratio between sodium hydroxide and sulfuric acid. And this is why you need the balanced reaction, because we get that from the coefficients in the balanced reaction, 2 and 1. So, sorry this is a little messy, but hopefully you are following. So now we're in moles of sodium hydroxide. We need to cancel that out, so that has to go in the denominator. So moles of H2SO4 goes up top. And we've got 1 mole of H2SO4 for every 2 moles of NaOH. Moles of NaOH, that unit cancels out. The only unit that's left is moles of H2SO4. Right? So and that's what we want, right? We can do that math, and when we do, we get an answer of for moles of 0.001477 moles of H2SO4. And we haven't finished our calculations yet, so you don't need to worry too much about sig figs yet. Right. So now we got that. Now, once again, we just need to convert the given volume to liters. So we can actually just do the exact same conversion that we did for the base. We got 25 milliliters. 1 liter over 1,000 milliliters. So we're just dividing by 1,000. That equals kind of a little cramped on the room there, but 0.025 liters. Alright, so now let's plug this value and this value into our equation for molarity. So the molarity of H2SO4 equals 0.001477 moles of H2SO4 over 0.02500 liters. Do that division, and we get a final answer of 0.05909 molar. And that was your concentration of the sulfuric acid solution. Again, titration problems will pretty much always follow that general type of format.